This is the GMAT 41. You are welcome to our basic organic chemistry class. In this class today, we are looking at the topic preparations and properties of alkynes. Alkynes is another unsaturated aliphatic hydrocarbons identified by the functional group triple bond. The functional group of alkynes is the triple bond. Take note, triple bond is represented by this carbon to carbon with 3 lines between them. Alright, it's also a covalent compound. Of course, we know generally that almost all organic compounds are covalently bonded compounds. Alright, in our previous class, we treated alkanes, and we learned that alkanes are also unsaturated hydrocarbons, but their functional group is what? Double bond. Now, in talking about alkynes, having known that they are unsaturated aliphatic hydrocarbons with the functional group triple bond, we want to look at the type of hybridization that alkynes undergo. Alkynes undergo sp hybridization. Is that okay? sp hybridization. And this sp hybridization leads to the formation of sigma bond and pi bond. Is that okay? In every alkyne molecule, we have a sigma bond, we also have pi bonds. Coming to the functional group carbon, there, one of the bonds there is a sigma bond. Is that okay? And then 2 others are pi bonds. The question now is, how is the sigma bond formed? Which is the strong bond there, and how are the pi bonds formed? Let us look at that. During the hybridization process, is that okay? Each carbon of the functional group will donate one sp hybridized orbital. So this carbon will donate one sp hybridized orbital, this carbon will donate one sp hybridized orbital. They will overlap axially to form the strong sigma bond. Now, how are the pi bonds formed? Alright, pi bonds, we know generally they are formed from unhybridized p orbital from each of the carbon atoms. Is that okay, of the functional group? So what happened in the case of sp hybridization? Because in sp2 hybridization in alkane we treated, each of the carbons of the functional group will donate one unhybridized p orbital. In this case of alkynes, each of the carbon of the functional group is donating 2 unhybridized p orbital. So this carbon will donate 2 unhybridized p orbital, this will donate 2 unhybridized p orbital. Now these 2 unhybridized p orbital from each carbon of the functional group will overlap laterally. Mind you that these orbitals are unhybridized. Is that okay? Now the lateral overlap of these unhybridized p orbital, 2 of them, will form the 2 pi bonds. Is that okay? They'll form the 2 pi bonds. Take note of that. In summary, when we come to the aspect of the functional group of triple bond, alright, in alkyne, what does that tell us? Every triple bond is made up of 1 sigma bond and 2 pi bonds. Take note of that. 1 sigma bond and what? 2 pi bonds. That's correct. Now, we want to look at the compounds from which we can get alkynes from which we can prepare, we can obtain, we can manufacture alkynes from. Here on the board, we have 4 of them we've listed. We can obtain alkynes from calcium dicarbide. Alright? We can also obtain alkynes from methane. This methane is obtained from petroleum, so we can get alkynes from them. We can also obtain alkynes from dihalogenoalkanes. You can see the compound here, CHX. The X here represents the halogens, alright? So 2 of them, dihalogenoalkanes. We can actually get alkynes from them. And then we can get alkynes from sodium alkynide. Alright, this method is actually used to convert smaller alkynes to larger alkynes. We're going to treat that when we get to that method. Now, in the next video, we are going to pick each of these methods one after the other and explain the process that leads to the formation of alkynes from them. Let us now look at the methods of preparation of alkynes. In the previous video, we already established the compounds from which alkynes can be obtained, and one of them is from calcium dicarbide. So when we look at how we can prepare alkynes from calcium dicarbide, the reaction is actually between calcium dicarbide and water. So the action of water on calcium dicarbide leads to the preparation of alkyne. Ethine is actually manufactured from this method. Is that okay? When water acts or reacts with calcium dicarbide, ethine is obtained. The chemical reaction is as shown on the board here. This is calcium dicarbide reacting with water. During the process, there will be a bond cleavage or bond breakage at this point between calcium and carbon, and then between hydrogen and oxygen. This carbon will react with hydrogen to give us ethyne. Is that okay? Carbon react with this hydrogen, we get ethyne. Take note that ethyne is the first member of the alkyne family. There is nothing like methane. Take note of that. Then this calcium would pick this oxygen to give us calcium oxide. Now, you might be required to establish the source of this calcium dicarbide. That is, where do we get the calcium dicarbide from, which actually reacts with this water to give us this ethyne. It's important for you to know that, alright? The calcium dicarbide is obtained from the electric furnace reaction between coke and calcium oxide. Once again, the calcium dicarbide is obtained from the electric arc furnace reaction. In the electric furnace reaction, coke reacts with calcium oxide. Coke is an allotrope of carbon. Is that okay? Coke is an allotrope of carbon. So it reacts with this quicklime, calcium oxide, in this electric furnace, and then calcium dicarbide will be produced. So that is how we actually obtain this calcium dicarbide that reacts with water to give us ethyne. Once again, you might be asked the source of this coke, as well as the source of this calcium oxide. Where do we actually get them from before we react them in the electric furnace to give us this calcium dicarbide? And the answer, this coke is obtained from coal. Coke is obtained from what? Coal. You can see the scheme here, is that okay? And then this quicklime, calcium oxide, is obtained from calcium trioxocarbonate 4, that is lime water. So this is the scheme here. You can see that coal produces coke. Limestone produces calcium oxide. Now in the electric furnace, this coke and calcium oxide will react to give us what? Calcium dicarbide. So you can answer how we got the calcium dicarbide from coke and calcium oxide. Then water will now act on this calcium dicarbide to give us our products, ethyne. Let us now look at the second method of preparing alkynes, which is the controlled partial oxidation of methane. Remember, one other compound from which we can obtain alkynes from is from methane. Methane obtained from petroleum. Is that okay? So the controlled partial oxidation of methane using air at a temperature of 1500 degrees centigrade will lead to the production of an alkyne. Ethyne in that case. Is that okay? Then we have other living groups, carbon dioxide and hydrogen gas will be given off during the chemical reaction. Please, it is very important for us to take into consideration the statement partial oxidation of methane. If you look at this product formed here, the product is no longer as the same as what we used to know when organic compounds undergo oxidation reaction with oxygen. You know, generally when, let's say maybe an alkane undergoes combustion, oxidation with oxygen, carbon dioxide and steam is usually formed. That occurs in complete combustion. It occurs in a case of complete combustion. That is why it's important for us to take note that this is a controlled partial oxidation. So you have to control the reaction in order to get the desired product. If you leave the reaction to itself, it's going to give us carbon dioxide and steam as the usual product of combustion. Is that okay? So looking at this, the controlled partial oxidation of methane will give us ethyne here, and then carbon dioxide and hydrogen gas. Does that make sense? So you can just go through the reaction equation. Please take note that this carbon dioxide and hydrogen gas given off here is of economic importance. Alright? It's of economic importance. Very, very important, because the carbon dioxide and hydrogen can react to produce alkanols. So please give attention to this note, which simply means that alkanols can actually be prepared when carbon dioxide and hydrogen gas reacts. In the next video, we're going to look at the other method of preparing alkynes, that is, from dihalogenalkanes. In this video, let us now discuss the third method of preparing alkynes, this time around from dihalogenalkanes, alright? The reaction is a dehydrohalogenation process, you know. Dehydrohalogenation simply means removing hydrogen halide, is that okay, from a given compound. So given a dihalogenalkane, through the dehydrohalogenation process, one can remove 2 molecules of hydrogen halide. Take note of that. How many molecules? 2 molecules of hydrogen halide. 2 molecules of HX will be removed from the dihalogenalkanes. Is that okay? And once these two molecules of hydrogen halide is removed from the dihalogenalkane, the resulting compound is the alkyne that we wish to prepare. But this reaction generally takes 2 steps. What are the steps? That is why you should get to know the reagents used for the dehydrohalogenation process. We encounter one of the reagents when we're preparing alkenes from halogenal alkanes using ethanolic solution of potassium hydroxide. So this is one of the reagents. If you treat the dihalogenal alkane with ethanolic solution of potassium hydroxide, what is going to happen? It will remove 1 molecule of hydrogen halide. It will remove what? 1 molecule of hydrogen halide. When this 1 molecule of hydrogen halide is removed from the dihalogenal alkane, what is going to be formed? A halogenal alkene will be formed. Take note of that. Halogenal what? Alkene will be formed. You know, you removed 1 molecule of a compound, which is equivalent to 2 atoms, hydrogen and what? The halogen. You removed it from the dihalogenal alkane. So on removing it from the dihalogenal alkane, since it's just 1 molecule you removed, which is 2 atoms, alright? An alkene will be formed. That alkene will contain 1 more halogen, because it's only 1 halogen removed in the first case when you treated it with potassium ethanolic solution of potassium hydroxide. Now, the formation of this halogenal alkene requires a stronger base to remove another molecule of hydrogen halide, which will make it what? 2 molecules of hydrogen halide all in all. And what is this stronger base that is required? The stronger base is sodamide in liquid ammonia. Alright, a stronger base is required, which is sodamide in liquid ammonia. It is this sodamide in liquid ammonia that will remove the second hydrogen halide from the halogenal alkene formed as an intermediate. Once the second hydrogen halide is removed, then the alkyne that you wish to prepare will be obtained. So take note, it's a 2-step reaction. First, you use ethanolic solution of potassium hydroxide to remove 1 molecule of hydrogen halide, and then next you use sodamide in liquid ammonia to remove the second molecule of hydrogen halide, giving us our alkyne. We have this reaction on the board here. Let us quickly explain that. Is that okay? Now, in this reaction, as we see here on the board, this compound is 1,2-dibromopropane. 1,2-dibromopropane. It's a dihalogenal alkane. So during the reaction, what is going to happen? This bromine will be removed. Is that okay? This bromine will be removed with 1 hydrogen from here. So let me put -1H. -1H. So this bromine with this 1 hydrogen that is being removed will give us the leaving group hydrogen bromide. Therefore, what is going to happen? As a result of removing 1 atom from this carbon and 1 atom from this carbon, you're going to introduce double bond between the 2 carbons from which you removed something. Is that okay? And you can see the product formed here. So this is the double bond between the 2 carbons where you removed bromine and the hydrogen from. So we introduced an extra bond. This compound has the name 1-bromopropane. This is 1-bromopropane. It's an alkene family. Is that okay? Halogenal alkane. Now, the ethanolic solution of potassium hydroxide is not strong enough to remove hydrogen halide from this 1-bromopropane. It's not strong enough. Therefore, we need a stronger base. And this is where the sodamide in liquid ammonia comes to play. So what's going to happen in the process? In the process, remember you are still removing another extra molecule of hydrogen halide. So what is going to happen here? This hydrogen will be removed. Is that okay? Then we'll come over here and remove this bromine. The hydrogen bromide goes off. Once again, take note that you removed something from this carbon, you also removed something from this carbon, so you are going to compensate for it by introducing another extra bond between the 2 carbons, making it a triple bond between the 2 carbons from which you removed the hydrogen halide. Now, the name of this compound is propyne. And of course, you'll be able to prepare an alkyne from dehydrohalogenation of dihalogenal alkane. Please take note that if we use only ethanolic solution of potassium hydroxide, the reaction will stop once we get the halogenal alkane, which is the 1-bromopropane in the case of our reaction here. Is that okay? So we always require sodamide in liquid ammonia to remove the second hydrogen halide. Does that make sense? Alright, so it's important for us to know. Just imagine that this reaction is given like this, with this potassium hydroxide in it and all. And then sodamide is not given. Sodamide in liquid ammonia is not given. This is the product you are going to get. So you stop here. Is that okay? But what if this reactant is given and then the reagent you have here is sodamide in liquid ammonia? That is, you didn't see anything like potassium hydroxide in ethanol again. You only saw sodamide in liquid ammonia here. Then your product you're going to get is directly the alkyne. Because it simply means that 2 molecules of hydrogen halide will be removed. Alright, and then you get your alkyne directly because of the use of this stronger base directly. In the next video, we're going to consider the preparation of alkynes from sodium alkylate. We're now going to look at the fourth method of preparing alkynes, this time from sodium alkylate. Alright, the reaction that leads to the formation of alkynes here is simply the reaction between sodium alkylate and primary halogenoalkanes. What's the importance of this method of preparing alkynes? It is used to convert smaller alkynes to larger ones. Is that okay? So take note of that. It's used to convert smaller alkynes to larger ones. So whenever you ask of the method used to convert smaller alkynes to larger alkynes, the method is the reaction of sodium alkylate with primary halogenoalkanes. Let us quickly look at how this reaction is being carried out. First of all is the preparation of the sodium alkylate. And how do we get the sodium alkylate? Please take note of this. Terminal alkynes is reacted with sodamide in ammonia. First, we say that the terminal alkynes is reacted with what? Sodamide in ammonia in order to obtain the sodium alkylate. So this is the first thing that is being done. What are terminal alkynes? Terminal alkynes are those alkynes in which the functional group, that is a triple bond, is found on carbon number 1. Terminal, end carbon, either the left or the right. So that's what we refer to as terminal alkynes. There are certain functional groups that we refer to as terminal functional groups. We have that in alkanals. We also have that in alkanoic acid. We also have that in acetamides. Their functional groups are terminal functional groups. They are always found on carbon number 1. That's the meaning of that terminal functional group. There are still other of the homologs that their functional groups are terminal actually. Alright, now having explained the concept of terminal alkynes, like we stated, the sodium alkylate is first obtained by reacting terminal alkynes with what? Sodamide in ammonia. Then once this sodium alkylate is formed, it's now reacted with primary halogenoalkane, and then we'll get the larger alkyne that we want to obtain. On the board here, we have the general scheme that shows the reaction. Look at this. This is the terminal alkyne. You can see that the triple bond is in carbon number 1. Then if you react it with sodamide, alright, sodamide in ammonia, we just choose to put ammonia here, although it's not absolutely compulsory. So if it's reacted with sodamide in ammonia, what's going to happen? There will be a bond cleavage at this point. This hydrogen will break off from this carbon. Then the sodamide would break up at this point, releasing this sodium. This sodium will replace this hydrogen here. So you're going to have R, C, triple bond, C, and A. This is the sodium alkylate. Is that okay? The hydrogen will react with this amine, NH2, to give us ammonia, NH3. Having obtained the sodium alkylate, the next is to react with the primary halogenoalkane, which in the process there will be a bond cleavage at this point still, and then this halogenoalkane will break at this point. Then this alkyl will take the position of this sodium. Please, this prime here, is just to tell us that this R may or may not be equal to this R here. That is, the alkyls may or may not be equal. Okay, so if this R prime takes this position, as the R prime takes this position, you will get the larger alkyne. So this is the larger what? Alkyne. Sodium will react with this halogen to give us sodium halide. Is that okay? So let us quickly look at an example here. This compound is propyne rather. This compound is propyne. So we want to see how we would obtain the sodium alkynide from here. In this case, sodium propionide. Is that okay? So we're going to react it with sodamide in ammonia. Reacting this propine with sodamide. The bond will break here. The bond will break here. Sodium will take this position to give us this compound. And this compound is our sodium alkynide. It has the nomenclature sodium propionide. Is that okay? So let me write that. This is sodium propionide. Good. Now this sodium propionide will now react with primary halogenoalkane. We have it here. Sodium propionide reacting. In this case, I use the butyl iodide or iodobutane. That is iodobutane. 1-iodobutane, or you can call it butyl iodide. So on reacting it with this sodium propionide, what's going to happen? Again, there will be a bond cleavage here. It's going to break up there. There will also be a bond breakage here. Is that okay? Therefore, this alkyl, which is butyl, would now take the position of this sodium. What are we going to get? Let's go. CH3, look at it. See here, look at it. Triple bond, look at the triple bond. Then this carbon, look at it. So this carbon now, this butyl will attach itself. In what order? Of course, you know that this CH3 cannot attach here. CH3 usually should come at the end. So this is how it will go. This CH2, from where this iodine was removed, that carbon would come and react with this carbon from where sodium was removed. Is that okay? So we're going to have CH2. You now start moving backward to this CH3. Another CH2, you can see that. Then another CH2, you can see that. And our CH3. Then sodium iodide would be the living group. This compound, let's find out the name. How many carbons do we have here altogether? I guess it should be 7. And the triple bond is closest to the left than it is to the right. So this compound is 7 carbon atom. The prefix is het. Is that also? So this is going to be het 3. Okay, this is het 2 because the triple bond is on carbon number 2 here. After the second carbon atom, you see the triple bond. So het 2I. Het 2I. So you see how we obtain a larger alkyne, het 2I, from a smaller one, propine, 3 carbons to 7 carbon atom. In the next video, we're now going to look at the properties of alkynes. First, a little tip about one important physical property of alkyne, and then we'll focus more on the chemical properties.